Okay, so we are going to solve the problem 1.3 of Griffiths' book on quantum mechanics, third edition. So what is this problem about? They give us a distribution, a probability density. It is written like this. This big A is a constant, have an exponential minus gamma. This gamma is a constant, x is the variable, little a is another constant, okay? And then there is a sequence of questions. They want us to obtain this A, okay? So first question is, what is this big A? Using equation 1.16. Equation 1.16 is this integral of the probability density, which we know has to be equal to 1. Sum of all probabilities has to be equal to 1. Then part B, we should obtain the mean of this variable x, the mean of the square, also the standard deviation. And part C is just to sketch this function. Okay, before we go on solving this problem, let's make a parenthesis here and talk a little bit about Gaussian function. Okay, a Gaussian function or a bell curve is given by this exponential with x squared. Okay, why is also known as bell function? No, bell curve, because at x0, this function is 1, okay? And as x increases, as the absolute value of x increases on the positive or on the negative side, since here we have x squared, this curve just decays. So it has this shape that looks like a bell curve. And we'll be using this function over and over again in this course to obtain expectation values, very similar to what this problem 1.3 is. So it's very important to know the integral of a Gaussian function. Okay, you don't need to memorize that. I'm just going to give you the answer. Whenever you have to solve that, this answer will be given to you. But in a future video, I'll explain where this answer comes from. Okay, but this integral from minus infinity to infinity is equal to square root of pi divided by what is here. Oh. So this is the solution. As I said, I'm going to explain to you in a future video where this comes from, but you don't need to know. Okay, this you will need to use it. Now, knowing that, we can come back to our problem. Okay, so knowing this, we come back to our problem. So first part is to use this integral to get the value of big A. So how do we do that? Well, A is a constant, so I take it out of the integral. Inside the integral, we have the function, which is a Gaussian distribution because we have that x squared. So this is a Gaussian distribution. Now to solve this, I'm going to do a change of variables. Instead of playing with x minus a, I'll play with u, which means that dx will become du. Okay, when x goes to minus infinity, also u does. So the range of the integral is still the same, minus gamma u squared du, which is that integral that I presented to you. What is the solution of this integral is what I just gave to you. So the solution will be square root of pi over what we have here, which is lambda. And this has to be equal to 1 because the sum of all probabilities is 1. Well, from there, you now get what this A is. Now, this big A is square root of gamma over pi. So let's keep this. We are going to be using it in the next questions. No, the next question is, first one, let's compute the expectation value, the mean value of this quantity. How do we do that? Integral of x and the probability density from minus infinity to infinity, which is big A, we know what it is. It's a constant, so let's keep it out. Inside the integral, we have x, and here the exponential, now which is lambda x minus a squared dx. Again, we are going to change variables. So again, we are going to use what we have here. Okay, so we're going to play with u. So there we go. The integral again remains from minus infinity to infinity. We said that now we are going to play with u. So that means wherever we have x, I'm going to substitute by u plus a, and this. All right. How do we continue? Now we have two integrals to solve. We have this integral. Oops, we already substituted this by u. So here we have u squared. So we have this integral to solve. And this other one. Little a is a constant. I can put it out. Correct this. Okay. All right. So this second integral, we are back to what we had before. This part here is just square root of pi over gamma, right? So we see that the solution from this part is just a. And from this other part here, don't waste your time. This is just 0. Okay, the solution then is the mean is just little a. Now, how do I know that this is just 0? And this is very important to know that this is 0. So you don't waste your time trying to solve an integral that is known beforehand to be 0. Why? Well, first, whenever you have an odd function multiplied by an even function, this is an odd function. Okay? Here, choose a different column. Here, this is an odd function. Okay, any polynomial odd with odd powers, u to the power 1 or u to the power 3, this is an odd function. Okay, so this is odd. This is a Gaussian. This is a squared, is an exponential with square. Because of the square, this is even. So this function inside the integral is an odd function. Okay, it's an odd function, and this integral is symmetric. Whenever you have that, you know that this is 0. Why? Well, let me give you an example of an odd function. What is an odd function? It's a function for which if you change the sign of x, the sign of the variable, you recover the same function, but with a negative sign. Okay, so what is an example of an odd function? X, the function x, in our case, the function u, or the function x is odd. Why? Well, let's make a plot of this function x. Okay, for x positive, I have this. Okay, for x negative, I have this. What is the integral? The area below the function, correct? So the area below the function here is positive. The area below the function here is negative. So this integral is 0. Okay, so don't waste your time solving an integral like this. Okay, it's 0. So very good. Mean value is A. Let's now go for the next question, which is now the mean of x squared. So how do we solve? Well, we put it in the integral. Now here, x squared of rho. Symmetric from minus infinity to infinity. Okay. Again, we are going to put big A outside. It's just a constant. We have x squared, exponential minus gamma x minus a. So it's always the same trick. We are going to change variables. And so x minus a will be now u. Du is dx. So there we go. This constant. Now, since we did this change of variables, x now is u plus a. So inside this integral, we have u plus a squared. Here we have, oops, I forgot the square here. Here we have minus lambda u squared du. Okay. All right, so now we'll have three integrals to solve. Now, if we open the square, we have three integrals to solve. What are they? U squared. Then we have 2UA, and we have finally plus A square I'm going to put outside. And let me do the same with this constant 2 and A. Let's put here 2 and A, and here just the variable. Okay. First thing to do, we've seen this before. This is odd. This is even. So this whole thing is odd. This integral is symmetric. We don't waste our time. This is 0. Okay. Now, this other one, we already did this before. We know that the solution of this integral is pi over lambda, not the square root of pi over lambda. Okay, so from this, we know that we get a square. Very good. Now, how about this part here? Well, here is not going to be 0 because this is even. Okay, even with even is even. So it's a symmetric integral, but of an even function. So how do we do that? So now comes a very interesting trick, which I would like you to know, which is the following. Let me just isolate that integral here. And look what we are going to do. I'm going to rewrite this as the derivative in lambda of this function. You see, when I do this derivative, what is going to come out? The minus u squared, which is what I have here, except for a sign. So to correct it, I put this minus sign. And so what I have here on the right is not the same thing as I have on the left. And then what we are going to do is at this minus, now this derivative, we are going to put outside the integral and first solve the integral in u. So this is a very nice trick to get rid of this u square from the integral. Okay? Well, this part we know very well how to solve. This is the solution. So you see that the solution for this integral is then minus the derivative in lambda of that function. Well, that square root of pi is a constant, so I can put it outside here. Don't need to worry about that. But the lambda, I cannot get rid of this. We have the integral, the derivative of that. What is the derivative of that? The minus half comes out. I get then plus 1/2. The square root of pi is just a constant. And here we have now lambda minus half minus 1 is minus 3/2. So this is half of square root of pi over lambda cube. Okay, so this is the this isolated integral, but remember we have this part in front of it. No? So this whole part here, let me rewrite, we have that constant in front, and the solution of that integral is this. So now we have to put together all pieces. We have this part and we have this part, correct? So putting all this together, the mean of x squared is going to be, we can cancel this, we can cancel this, and we have from this 1 over 2 lambda, and from this part we have plus a squared. Very good. We got the mean of x squared. The next part was then to get the standard deviation. Well, to get the standard deviation, let me start with the variance, which is the mean of x squared minus the square of the mean. Here we have 1 over 2 lambda plus a squared. This is this part, minus the mean. Let's go back all the way up. The mean is a, so the square of the mean is going to be a squared. So we have a squared, which means this cancel, and we got 1 over 2 lambda. So the standard deviation is 1 over square root of 2 lambda. All right, very good. So the last thing to do is just to sketch the function. So we know that the sketch of this function is bell shape. We just have to be careful because we found that the mean is not 0, is a for this function, no? Because we have here x minus a squared. So when we sketch that, instead of putting the center of this Gaussian in 0, we are going to put it at a. Okay, so then we have something like this around where this peak happens at a. And that's it. That's the solution of this problem. Again, a very, very important problem to know how to deal with Gaussian distributions. Okay, and I'm going to show in another video why the solution of an integral like this is this square root.